So, hi everyone. Welcome to the final session of this conference. It's my great pleasure to introduce the first speaker of this afternoon. It's Dixy Msapato from Leeds, and he's going to talk us about the Karoubi envelope of an extriangulated category. Go ahead, Dixy.
Thank you very much. So today I'll be talking about the Karoubi envelope of an extriangulated category. This work is based off a recent paper, which can be found in the journal, The Applied Categorical Structures, and the title there is a bit longer, the Karoubi envelope and idempotent completion of an extriangulated category. In that paper, I proved that the idempotent completion of an extriangulated category is again extriangulated, and likewise for the idempotent completion. That's what I'm saying that the authors Wang, Wei, Zhao, and Zhang have proved the same result, but with a very much different approach. The result is also known for the triangulated case, and that's proved by Bohmer and Schlichting, and it's an exact case proved by Buehler. And essentially, the three papers take the view of Bohmer and Schlichting, and in there, the description of the triangulated structure is less explicit. And in my paper, I give a more explicit view of the structure, and that's what I want to outline in this talk. Line of the talk is as follows. I'm going to start by introducing idempotent completion, and then I'll talk about the Karoubi envelope, also known as the idempotent completion. Then I'll quickly review the theory of extriangulated categories. Then I'll give an explicit structure of the extriangulated category on the Karoubi envelope. And I'll compare this with the triangulated case and show how it's different and how it's similar. And if time allows, I'll talk about the weak idempotent completion and close up with some remarks. So to start with, we're going to be working in an additive category. An object X of an additive category is called an idempotent if, a morphism E on X is called an idempotent if E compares with E gives you back E. So an additive category A is an idempotent complete if every idempotent morphism E from A to A gives you the composition of the domain object A into two objects K and L, such that with respect to this composition, E is isomorphic to this matrix here. An equivalent formulation of what it means to be idempotent complete, which you may have seen, says that A is idempotent complete if every idempotent has a kernel. As a kernel. And you can sort of see how this equivalent formulations are sort of related by, for example, well, in this decomposition here, this K would be the kernel to E, and this L will be the kernel to the other idempotent 1 minus E. So if E is an idempotent morphism, so is 1 minus E. So this is how these two formulations are related. Idempotent completeness is something that comes up a lot in literature, and in fact, this work was originally an offshoot of something else I was working on at the time, and I wanted to assume something was idempotent complete. Just to sort of convince you that it's something maybe you should care about. If you don't, I just want to show you what appears in some of the literature and to sort of like emphasize its importance. So, for example, there's a theorem by Krauser from 2015 where they proved that an additive category A has a Karoubi property if and only if A is an idempotent complete, and the endomorphism ring of every object is semi-perfect. By being a Karoubi category, I just mean that every object X is a direct sum of indecomposables. So it's what you might already think indecomposable. Another place where I've seen it is in the definition of an abelian category. So Hasse introduced an abelian categories as high homological versions of abelian categories, in the sense that one abelian categories are precisely abelian categories. And it's known for abelian categories that they are idempotent complete. But if n is greater than t, the other axioms are independent of idempotent completion. And one consequence of having idempotent completion in any abelian categories is that we have the existence of n push-outs. All right. So if you're given an additive category A, it's always possible there exists a category, let's say A tilde, called the Karoubi envelope, which A embeds into, and A is idempotent complete. So this is called the Karoubi envelope or idempotent completion. And it has a nice explicit construction, which I'll go over on the next page. So we start with an additive category A. The Karoubi envelope, which I'm going to write A tilde, is defined as follows. So the objects of A tilde are just pairs of an object A and a morphism P, which is idempotent. A morphism between two objects of A tilde, say AP and BQ, is just a morphism in the underlying category A with the property that a morphism sigma, such that sigma composed with P is the same as Q composed with sigma, and which is just sigma again. Given an object AP in the Karoubi envelope, the identity on AP is just given by the morphism P again, so the same P. So the Karoubi envelope has the following properties. So it's idempotent complete. It's an additive category. And the byproduct in A tilde on two objects AP and BQ is just given by the component-wise direct sum. We have an embedding from A to its Karoubi envelope, A tilde, and this is faithfully additive. And it's defined by mapping an object A to the pair A with identity on A, and F just goes to F. And the Karoubi envelope is universal in the sense that if we have another idempotent complete category B and a functor from A to B, then this functor F, then there exists a functor F tilde such that F factors through F tilde. So more formally, there exists a natural isomorphism from F to F tilde composed with the inclusion. So in order to talk about my main theorem, I need to talk about extriangulated categories. This is just going to be a really quick overview, but if you're not aware of extriangulated categories, they generalize simultaneously exact categories and triangulated categories. So if you're unaware of extriangulated categories, then I urge you to think of your favorite exact category or your favorite triangulated category. And as we go on, I'll explain how these are extriangulated. But to begin with, I need the following definition. So given T sequences of morphisms, A, B, C, and A, B prime, C prime, so that these sequences are equivalent if there exists an isomorphism B from B to B prime, such that the following diagram commutes. And this gives us an equivalence relation, and we denote by square bracket a BC square bracket the equivalence class of the sequence ABC. So it's definition by Naka-Akampali. So an extriangulated category is a triple C, E, S, where C is an additive category. E is a bi-additive functor on C up across C up. So E can be thought of as the X functor basically. So in the triangulated case, this blackboard E is just the hom functor with a shift. In the exact case, is just the X1 functor. So the third axiom is that this S is something called a realization, and what it does is it assigns to, so the elements of this bifunctor has their abelian groups are called E extensions, and S assigns to every E extension delta an equivalence class of morphisms. So in the triangulated case, delta, for example, would be a morphism from C to a shifted. So S we just assigned delta a triangle, some triangle ABC. And the other axiom is that we have an octahedron axiom, a bit like the one in the triangulated case. So just some notation. So let's take two objects A and C, and let's take an E extension delta. Because E is a bifunctor, for a morphism A from A to A prime, we can define another E extension by taking delta and applying it to the homomorphism, the group homomorphism EC to A. And we're going to denote by A star delta, A underscore star delta, this E extension we get. And dually, we start with the morphism C from C prime to C. We're going to write C superscript star of delta to be the E extension we get if we apply delta to this homomorphism. And actually, just to say, this can be thought of as the extension you get by taking push-outs. And this can be thought of what you get if you take pullbacks. Push-outs along triangles or exact sequences. And push, yeah, likewise. So given two E extensions, delta and delta prime, we can define a morphism between delta and delta prime. And this is just a pair of morphisms in the category from A to A prime, C to C prime, with the property that A underscore delta is equal to C superscript delta prime. Right. So the next thing I want to talk about is the relative theory of extriangulated categories. So we start with an extriangulated category C, CES, and we say we have a functor F from C up to C to the abelian category again. Then we say that F is an additive subfunctor if for any two objects C and A, FCA is a subgroup of ECA, and if for any two morphisms A and C, the group homomorphism FCA is just the restriction of the group homomorphism ECA to the subgroup FCA. Given some additive functor F, we would say that F is closed if given an E triangle. So this, again, just think of this as the extriangulated version of a triangle. If we apply F to any triangle, then we get the following sequence, the following exact sequence of natural transformations. And the main result of the relative theory of extriangulated categories is as follows. So let CES be a triangulated category. And suppose we have a functor F, which is an additive subfunctor. Then we can define a new extriangulated structure on C, given by CF, and S restricted to the F extensions, if and only if F is closed. All right, so at this point, we can state the main theorem of this talk. So let CES be an extriangulated category, and let C tilde be the aneuploidy completion of C. Then the aneuploidy completion of C is an extriangulated category, which has structure given by C tilde, F, and R. I'm going to talk about what F and R are shortly. Moreover, the natural embedding from C to the Karoubi envelope idempotent completion is an extriangulated functor. An extriangulated functor is just a functor between two extriangulated categories which preserves the extriangulated structure. So something like an exact functor in the case of a triangulated category or exact categories. So the theorem says that we have an extriangulated structure on the Karoubi envelope, C tilde. So I want to tell you what this structure is explicitly. So I have to define, first of all, the bifunctor F, which would be on C up cross C to ab. So for two objects, xp and yq in C tilde, I'm going to define F to be the following set. So it'd be P star, Q star of delta, where delta is an element of the xy. So to be more specific, it's just the image of the group EXY under the homomorphism. Following homomorphism. So it's the image. So given, okay, so I now have to define F1 morphisms. So given a pair of morphisms, alpha tilde and B tilde, I'm going to define F of alpha opposite tilde B tilde to be just the restriction, to be this thing. And it turns out to be the restriction actually of this homomorphism onto the group XP on YQ above here. So the interesting thing about F is that it very much behaves like a closed additive subfunctor of E, but it's not a closed additive subfunctor because F and E act on different domains. Whereas he's on this, right? But other than that, it pretty much has a property, the properties of unclosed additive subfunctor. So what do I mean? Well, given two objects CP and AQ, FCP and AQ is a subgroup of ECA. Given two morphisms C and A, which remember are just morphisms in the underlying category. This group homomorphism is just a restriction of ECA on this group up here. And it turns out that given an F triangle, XQ, YO, and ZP, the following sequences of natural transformations are exact. And you can prove this fact without really, before you even prove that C tilde is extriangulated, which is quite unusual because usually you need to prove that first to get these results. And this observation turns out to be quite useful actually in the proof of the axiom 84, the octahedron axiom. In proving this, I was able to essentially use the relative theory, which I have. It's not by the strict sense to prove this. The axiom, the octahedron axiom, which is usually the hardest axiom to prove. Okay, so our goal is just to remind you is to prove that we have an extriangulated structure. So far we've dealt with the functor F. So the next thing we need to do is define the realization R. But to do that, the following lemma is crucial. So let AGT be a triple satisfying the axioms of an extriangulated category except for the octahedron axiom, so ET0 to ET3. Let delta be a G extension, which is realized by ABC. And let EF be a morphism of G extensions, where E and F are idempotent morphisms. So essentially, we're in a situation where we have an E triangle, and E and F are idempotent. Then the lemma says there exists a G such that G is idempotent, and the following diagram commutes. Okay, so how do we define it? So remember that our F extensions are just E extensions because they're images under the E extension homomorphisms. So given given an F extension delta, which lives in FZP XQ, we know that delta is going to be of the form P star Q star epsilon for some epsilon in E of ZX. And because we see S is an extriangulated category, we can assign this to an equivalence class XYZ. So in the idempotent completion, we assign delta, the same extension, to the following equivalence class, XQ, YR, and ZP, where R is an idempotent morphism satisfying Rx is equal to XQ and YR is equal to PY. And to get R, essentially we just apply the previous lemma on XYZ. So in defining R, you may have noticed that this depends on two choices. It depends on the choice of the idempotent R and the choice of the representative of this equivalence class here. And it turns out that R is well defined in the sense that if you take a different representative of the equivalence class or a different idempotent here, what you get back is an equivalent thing. So there's nothing to worry about there. So our definition is quite different to what's been done in other cases. For example, the triangulated case. Here we have a very explicit description of what the X triangles are. But for example, in the triangulated case, the description is not quite as explicit. So in fact, when Baum and Schlichting did it for the triangulated case, they said that a sequence of morphism is a distinguished triangle if and only if it's a direct summand of an image of a distinguished triangle from C under the embedding. But it turns out that our description and this sort of description is really not too different in the sense that if we're given it an F triangle, A, Q, B, R, CP, then there is another F triangle such that their direct sum is isomorphic to the image of an E triangle under the embedding here. So in this sense, our main result is a unification of similar theorems in the exact triangulated case. And by unification, I mean that if you, for example, started with a triangulated category C sigma delta, then by a result of Baum and Schlichting, we get a triangulated structure on the Karoubi envelope. But you can also go this way. By a result of Nakaoka and Pali, given this triangulated category here, we have an extriangulated structure, CES. And by my result, the Karoubi envelope has an extriangulated structure. And by Nakaoka and Pali, there's a triangulated structure on this extriangulated category given by C tilde, sigma tilde, and theta, where this is just some other distinguished triangles. But it turns out that these things are equal. So it's a unification in that sense. And the same statement holds for the exact case. I don't have much time left, so I'm going to skip what I was going to say about the weak idempotent completion. But if you know what that is, we have to find a theorem which says that let C as being an extriangulated category, and where C is a small category as well. This is needed to define the weak idempotent completion and the smallness condition. Then let C tilde F be the idempotent completion, which we've shown is extriangulated. Then it turns out that the weak idempotent completion, C hat of C, is an extension closed subcategory of C tilde. Hence, C hat is itself an extriangulated category. And just to quickly, actually, just show you how you define the weak idempotent completion actually before, because I have like an extra second. Essentially, the construction of the weak idempotent completion is quite similar to the Karoubi envelope, except that you require your idempotence P to split, whereas in the Karoubi envelope, it's just any idempotent. Thank you very much. I hope you enjoyed that.
Thank you